Okay, so today, obviously, we're slated to finish chapter 18, which is our last chapter. It's on ethers, and I'm hoping that after the previous class, I've managed to convince you guys that, with one notable exception, ethers are quite unreactive. You've got to go as far as to basically heat them up with pure HCl, HBr, HI in order to get them to react. And even then, remember, aromatic and vinylic ethers don't react. So they're quite unreactive. No wonder we so often use them as solvents. It's kind of nice for our solvents to be pretty unreactive. And of course, the major exception to all this is epoxides, which are special because they're three-membered cyclic ethers, and as such, they're susceptible to nucleophilic attack in both acidic and alkaline medium. And that's going to be one of the, probably the main thing that we talk about today. It's going to be a good time to review the idea of being in an acidic medium, being in an alkaline medium. How do you know which you're in? That's going to be a really important topic next term as well. And so certainly we'll go over all that as well. But whether we're in acidic or alkaline medium, epoxides are quite susceptible to nucleophilic attack. And you get ring-opened products having broken open the three-membered ring, which, as you can imagine, releases a tremendous amount of energy from all of that ring strain, and you can get some nice stable products that way. Yep, you do have epoxy resins. I feel like I remember there being some sort of pathway that uses epoxides. Anyway, but yes, epoxy resins are a thing. We'll talk about things like that next term also. That will be actually the last day of Organic 2. That will be the day that all of you who are majoring, rather than planning on going to medical school, you're majoring in engineering or material science, and you're in the minority, but it's not like there's one or two of you. You know, it's probably 15, 20% of you at a conservative estimate. And you have to be, you're terribly patient, both terms. That last day of class in Organic 2 is all for you, because we're going to talk about polymers. Anyways, so here's an example of a reaction that involves ring opening of an epoxide that will be happening in acidic medium, as you can tell just by what we're given. And you would do it by dissolving this epoxide, namely styrene oxide, in methanol and adding a little bit of maybe sulfuric acid or something like that. And of course, technically, we do have a chiral carbon here, so I would expect this would be a racemic mixture. Again, read the problem carefully as to what you have to show, but any stereochemical outcome in the product I would expect would also be, you would also get a racemic mixture. That's the only that's the only chiral carbon, so we don't have to worry about diastereomers or anything like that. So one thing that we can hopefully all recall about acidic medium is that when we're in an acidic medium, we must be very careful in our mechanisms not to invoke any strongly basic anions. So no OH minus, no alkoxides, no NH2 minus, certainly no carbanions, nothing like that. Those things cannot exist in an acidic medium. They would immediately react with the surrounding acid. So that means we need to be careful when we draw our mechanisms. And something we've seen already about carbon-oxygen bonds in reactions that are in acidic medium is it's pretty commonplace to protonate that oxygen before any kind of nucleophilic attack. We saw that already in the context of carbon-oxygen pi bonds, namely carbonyl groups. So the same thing is true even of carbon-oxygen sigma bonds, like in this case. And we're going to have a ton more to say about carbonyl chemistry next term also, as I believe I've mentioned. And all that makes sense, by the way, because if our nucleophile just attacked our epoxide and opened the ring, you'd wind up with O-, and that's no good. You can't invoke intermediates like that in an acidic medium. They're too strongly alkaline. The only anions that you can consider as being okay in an alkaline medium are the conjugate bases of very strong acids. So things like Cl minus, Br minus, HSO4 minus, NO3 minus. These are the conjugate bases of HCl, HBr, sulfuric acid, right? Nitric acid, really strong acids. So those anions are okay in acidic medium. They're not at all strongly basic, quite the opposite. But anything like OH minus, oxygen with a minus charge, nitrogen with a minus charge, carbanions, those are no good in acidic medium. We cannot invoke species like that because they can't exist in acidic medium. So the first thing we're going to want to do is put a proton on that oxygen. But that then begs another question, which is, what are we going to use to do it? And so another thing that you need to know about acidic medium, particularly when you're working with a protic solvent, which we certainly have here, you need to know that you're going to also have the conjugate acid of whatever your solvent is. And it might say H plus here, it might say H2SO4, H3PO4. Generally, it's done by adding a catalytic amount of some strong inorganic acid, but you need to know that. You need to know what you're going to get as a result is the conjugate acid of your solvent. That's going to be the effect of dissolving a little bit of acid in there. These strong acids, whatever they may be, sulfuric acid, phosphoric acid, they're going to dissociate completely and donate their protons to molecules of the solvent. Not all of them, of course. Most of the methanol molecules at any one time will not be protonated, but some will, and that will come from dissociation of your acid catalyst. So you're going to have some of whatever the conjugate acid of your solvent is. Just like if water were our solvent, which it might have been, then you'll have some H3O plus present. So this is the same thing, except instead of water, we happen to have methanol. If we'd had ethanol instead, you'd have the conjugate acid of methanol. If isopropanol, you'd have the conjugate acid of isopropanol, etc. So another point, I made this pretty often in the previous class, I mean, section 504, right before you guys, that this is why I'm always saying, knowing what to put here is not something you memorize beforehand. You cannot succeed at this subject if you insist on always approaching it that way. It's not something you've memorized beforehand. It's something you figure out at the time based on what you're given. And here we're given methanol. And the conjugate acid of methanol looks like this. So you do need to think about what the conjugate acid will look like, especially if you have water or an alcohol solvent or something like that. So that's what we're going to use to put the proton onto that oxygen. We will just take a proton off of the conjugate acid of methanol, and now we've protonated our epoxide oxygen. Looking something a little bit like this. That's a plus charge. And now we're ready for our nucleophilic attack. And the next thing you need to know about ring opening of epoxides under acidic conditions is that the nucleophile will attack in the more hindered position. And in a few minutes, I'll show you why that is. And you need to know why it is in order to understand it well enough to remember it later on. So that, of course, begs yet another question, namely, what's our nucleophile? Again, whenever you want to answer such questions, what do I put down next? Always go back and look at what you're given. That's how you make those decisions. The only nucleophilic species here is methanol, right? We can't have CH3O minus, for instance, not in an acidic medium. Alkaline medium, maybe, not acidic medium. So that's going to be our nucleophile. And again, for reasons which we'll get to in just a couple minutes, our nucleophile is going to attack the more hindered carbon. And in so doing, we'll break open that three-membered ring and release a tremendous amount of strain energy. So I would expect this next intermediate, we're not quite done yet, this one's still going to have a plus charge. So I think it will look like this. And now we have OH over here. And so now, I should mention, by the way, this step here is nothing other than an SN2 reaction. So we're already well familiar with processes like that. Our nucleophile comes in from behind our leaving group. We kick out the leaving group. The leaving group is essentially this OH group with a plus charge. We break that carbon-oxygen bond. That represents the leaving group leaving. Of course, over here on this carbon, there's no chemistry happening. So that CH2 is just along for the ride, just lines up in the product. And so the next intermediate looks like this. And so now again, we want to get to a neutral product. That's another important thing to know. And so we should be asking, what can we use to pull that proton off? And again, you don't memorize it's H2O or some such thing. You need to look at what you're given. And again, the only thing we have around is methanol, so that's going to have to act as our base. And then an acidic medium, an alcohol molecule is good enough. By the way, in case you were at all uncomfortable with this structure over here at the beginning, you'll notice we just made one of those. So this is an acid catalyzed process. No protons are consumed during the process. And once you've got that, then we've got our final product, which will, of course, be an ether. Looking something hopefully like this. And again, I would expect this would be racemic. We do have one chiral carbon. I'm assuming we're starting with racemic epoxide, so I would expect a racemic product. Again, this carbon over here is not chiral. That's a CH2. So the wording of the question will tell you how you need to show that. The OWL will not infrequently say, don't even worry about stereochemistry, in which case something like that will be just fine. They might do what I usually do, which is draw one of the two enantiomers, in which case flip a coin in your head and decide whether you want to make that a wedge bond or a dotted bond. Or they might say, knowing OWL, they might sometimes say draw both enantiomers, in which case you'll draw both enantiomers. Good, so that's one example of this. And we're going to do another one, but I want to address the question first about why the nucleophile attacks in the more hindered position. Any questions before we go there? What I'm going to do is just redraw that intermediate. There we go. And so what I'd like us to notice about this structure is, yes, there's a plus charge on oxygen, but the two carbons are also helping the oxygen to bear the plus charge. And that's nothing new for us. We saw the same thing in halogenation of alkenes and halohydrin formation from alkenes. So it's the same type of idea. There you also had a three-membered ring with a plus charge on a halogen atom, but the carbons did help to stabilize it. So although you didn't have full carbocations, there was some degree of plus charge on those two carbons. So the same thing is true here. And I think you'll agree, of these two carbons, the one that is more substituted, the one that is more hindered, it would make sense that that would have more plus charge on it than the one that is less substituted. Because we know that other things being equal, carbocations get more stable the more substituted that carbocation carbon gets. You could, even without doing any big violence to the situation, you can even consider this species to be resonance stabilized. I mean, I think you're looking at pretty minor contributors. But one of them might look like, whoops, that's not plus any longer, is it? One of them would look like this, with a plus charge on that carbon. These are sort of bond-no bond resonance forms, which we haven't seen too many of yet, but I don't think they're anything too mysterious. You'll then have another resonance form where the plus charge is over here, just CH2 plus. And so, of course, this one here is going to be the major contributor. But I think you'll agree it makes sense for there to be more of that in the mix in the hybrid than of this one. Because here the plus charge is at least in the secondary carbon. Here it's in the primary carbon. So that's the reason why the nucleophile attacks the more hindered carbon, because that carbon has more partial plus charge on it. So, and again, you need to know that in order to understand this. Don't refuse to learn these reasons as to why things happen the way they do. They're the key to your succeeding in organic chemistry. And this is something that we don't have to pull out any radically, hugely difficult quantum mechanics or something like that. This is something that we can understand just based on the valence bond model. So there's nothing too crazy here. So that's why in an acidic medium, given an unsymmetrical epoxide, of course, where one of the carbons is more hindered than the other, that's why your nucleophile will attack the more hindered carbon under acidic conditions. And we'll do another example of these. So this is the major product. These things here are not products. Those are resonance contributors. And I think the major contributor will be this one, right? Because the plus charge is in the oxygen and everything's obeying the octet rule. But of the other two, I think there's going to be more contribution of this one than of this one, because this one at least has the partial plus charge and a more substituted carbon. This one has a partial plus charge in the secondary carbon, this one on a primary carbon. So I think it's mostly looking like this, but there's going to be more of this than of that one. At least that's what I would think. And so that's the explanation of why when you open an epoxide under acidic conditions, and we're going to do another whole example, by the way, that's why our nucleophile attacks in the more hindered position under acidic conditions. Make sense? Other questions on that before we do another example? Or while you think about that, maybe I'll even come up with another example. Let's go crazy. Let's treat this with butylamine with a little bit of acid, maybe a little bit. It might say H2SO4, you know, it might mention the kind of acid. Doesn't matter as long as it's some strong inorganic mineral acid. But you can certainly do a ring opening like this too. So again, now we need to think what's going to be the conjugate acid of the solvent. I can tell by what I'm given that I'm under acidic conditions, whether this was given to me as H plus or H2SO4. I can tell that we're under acidic conditions. That means that the first step, I'm going to need to use the conjugate acid of whatever my solvent is, my protic solvant, typically it's a protic solvent, in order to protonate the epoxide oxygen before we can do the ring opening. And again, the reason bears repeating. The reason we needed to put the proton on first is if the alcohol had just attacked over here, if the nucleophile had just attacked, we would get O-, and that's no good, not in an acidic solution. Alkaline, that's fine. Acidic medium, not so much. So that's why we put the proton on first. And again, don't refuse to learn these reasons. They are the only way to succeed in organic chemistry, at least in my opinion. At least that's what I've observed after teaching it for a bunch of years. So we're going to do the same thing again. We're going to look at the conjugate acid of our solvent. So the butylammoniumine, Bu is butyl, CH2, 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 CH3. And that's what we're going to use to protonate this oxygen. Same as before. So now there's a plus charge in the oxygen, and now our nucleophile can attack. That's going to attack in the more hindered position again. Which I think you'll agree is that carbon, for reasons that we've previously stated. so now we'll have OH over here. And this ammonium salt over here, that's an N, although it would be understandable if you would have trouble telling that. And so now all we need to do, just like we did before, is pull off this proton in order to give us a neutral product, and we're done. How do I know what to use? Again, it's not memorized beforehand. Whenever that question comes in your head when you're doing a problem, how do I know what to put down next? The answer generally is go back and look at what you're given, and that will help you to decide. The only thing I've got around that can pull that proton off for me is butylamine. There is nothing else. And so that's what we'll use. We'll pull that proton off, put the electrons on nitrogen, and I would predict that our product would look something like this. Something like that. Of course, any number of other correct ways to draw that. So that's acidic solution. We also need to consider what epoxide ring opening looks like in alkaline solution. And that's where we're going to go next. Good. Any other questions before we do that? And as usual, this is going to go on YouTube. I'm going to try to do it today, actually, since I want to save tomorrow for things involving your exam and maybe my 222 exam. So you'll be able to pause whenever you like, replay things. Good. Let's, I'm going to try this. Delete. We almost worked. Okay. So what about under alkaline conditions? Here, we'll find that the nucleophile attacks in less hindered position. And we'll do a couple of examples of this type of reaction also. And we'll go over why that is also, but I can give you a preview of what the answer is going to be. The difference here is that we won't get any cationic intermediates. And that makes sense since we're an alkaline solution. Remember, in acidic solution, we said we don't want to see any strongly basic anions. We can't invoke anything like that during the course of the mechanism, because those things can't exist in acidic solution. In alkaline solution, we turn the idea on its head. And here we don't want to see any reactive cations. So no carbocations, no H3O+, no other oxonium ions, not an alkaline solution. In acidic solution, yes, not an alkaline solution, because those reactive cations couldn't exist. They would be immediately protonated, deprotonated by the alkali that's present in the solution. So no reactive cations in an acidic medium. The only cations, if you want to know what sort of cations you can have in alkaline medium, the only ones that make any sense at all are metal cations, Na+, K+, Ca2+. Not that we'll be doing anything with those anyway in terms of the mechanism, those are all spectator ions. So just like in acidic solution, the only anions you can have around can be the conjugate bases of very strong acids, which you're not likely to be using in your mechanism anyway. In alkaline solution, the only cations that can survive are metal cations. So let's consider an example of one of these under alkaline conditions. We'll go back to our styrene oxide. And this time, we'll treat it with something alkaline, like what about sodium methoxide in methanol. So again, what you need to know whenever you see a formula like this is that what you're essentially looking at is the methoxide ion, right? This is this, right? Because the sodium cation is just a spectator ion. It's not going to play any role in the chemistry. There are no arrows involving it. It's just a spectator ion. It plays the role of a countercharge, but that's it. It's not involved in the actual mechanism. So that's something you need to know about ionic compounds. Especially these alkali metal salts, the alkali metal ion is not involved in the mechanism. So this is this. And I could have given you any other such anionic species, but some alkoxide in the corresponding alcohol as the solvent, that's pretty common. We'll do a second example after this too. And so, in this case, what you need to know is that when you're in alkaline solution, which again, I would expect you to be able to tell in this case, based on what we're given, I'm given an anion here. So there's no acid around. That means we can't use any, certainly any strong Bronsted-Lowry acids in our mechanism, no H3O plus or anything like this. And not only that, we'd better not invoke any carbocations or oxygen with a plus charge or anything like that. Just anions. And so, since we're in alkaline solution, we will not protonate that oxygen first. We'd better not, because otherwise we'd wind up with an oxygen with a plus charge, and that doesn't make sense in alkaline medium. So what happens under alkaline conditions is our nucleophile attacks in the less hindered position only because now it can. There's no other structural issue that limits it. Before, we had all three atoms in the three-membered ring bearing some plus charge. So it makes sense that the nucleophile is going to attack where it has the most plus charge. Here, there's nothing like that going on. There's no plus charge anywhere. So the nucleophile will just go where it has the most room. And by the way, this once again is an SN2 step. So we understand that mechanism fully. The nucleophile comes in from behind the leaving group and breaks that bond. And so what are we going to get? Looks to me we're now going to get O- over here and OCH3 over here. And now we're perfectly fine having an oxyanion. We're an alkaline medium. We can rationalize having an intermediate that looks like that. And so all we need to do now in order to get a neutral product is reprotonate that oxygen. And that means we have to look around for something that can act as a Bronsted-Lowry acid. And again, I can't keep stressing this enough. This is not something you'll have memorized ahead of time. You cannot learn this material that way. You always need to consider each case on its own merits. And so it's not something you'll have memorized beforehand. You'll always go back and look at what you're given in order to figure out the answer to the question, what do I put down now? In this case, the only species that can act as an acid at all is that alcohol as your solvent. So that's what we'll use. And that's going to put the proton back on that oxygen for us, and then we'll get our final product. Which again, I would anticipate would be a racemic mixture, assuming that we started with racemic epoxide. So again, the wording of the problem will tell you how you need to put that down. Good, so and another thing, just as always under alkaline conditions, those mechanisms always to me seem more straightforward than the mechanisms in acidic medium. In cases like this where you can go either way, I find the alkaline version is less steppy and more straightforward. So we'll do another example besides this, but any questions on this mechanism? So bombs away. The nucleophile just goes ahead and attacks in the less hindered position because there's more room there, and there's no structural feature that limits where it should go. Before, we had an issue with partial plus charge on a carbon atom. And so no wonder the nucleophile would be more attracted to the carbon that has more plus charge on it. Here, there's no such issue. So it just bombs away, goes right for the place where it has the most room. Let's do another one. Oh, wait a minute. Actually, let me make it a 5-membered ring. Just because I feel like making it a 5-membered ring. Let's say that we started with this epoxide, and we need something alkaline. Oh, what about the conjugate base of a thiol? We'll use Bu for butyl group again. So that's the conjugate base of butane thiol, which you could easily make by adding sodium hydroxide even to butane thiol. That would not work for an alcohol, right? Alkoxide, or rather hydroxide ion cannot anything near quantitatively deprotonate an alcohol because they're similar in, alcohols and water are very similar in acidity. But thiols, you'll recall, are very much more acidic than alcohols, other things being equal. So you don't need to go as far as NH2- or H- or one of these things like you did with an alcohol. You can use those other ones. It's not wrong, but you don't need to. You can get away with a much weaker base. So that thiolate ion would be very easy to make. Now, the one that I copied this problem off of gave as my solvents a mixture of ethanol and water. And I have to assume, because that mixture gives the best solubility, other things being equal. So, but I would expect you to look at this and to be able to tell this is an alkaline species. It's an anion. Right? So we're under conditions where anions are going to reign supreme. We're not going to have any cations, no carbocations, no oxonium ions. But it also means that since we're under alkaline conditions, our nucleophile will just attack the less hindered carbon, again, because there's nothing structurally that's going to make it need to do otherwise. So it'll just go where there's more room. This again is going to be an SN2 step. So I would expect that we'd have O- over here. Actually, that doesn't look so good. I think it would look better to draw it more like this, O-. And the reason I know that this wedge bond stays the same is because this carbon atom is not involved in the mechanism. The chemistry is occurring over here. This carbon-oxygen bond is just along for the ride. So that oxygen is going to stay on a wedge bond. This one will come in from behind, and I would expect would look something like this. And yeah, if you wanted to draw the hydrogen also, you can. You don't have to, but you can if you want. It's understood. So you're going to have this intermediate, and now we just need to figure out what's going to put the proton back on this oxygen for us. I don't know. I don't have it memorized beforehand. So I'll look at what I'm given. And of these species, the most acidic one is water. So that's what we'll use. Water is a little bit more acidic than ethanol. So that's what I think we should use. And so I would expect our final product would look something like unto this. And again, you can show the other hydrogen on the wedge bond if you want to. You don't have to, but you can if you want to. It's understood. So bottom line, when we're doing a ring opening of an epoxide in alkaline conditions, now we can invoke strongly basic anions like oxyanions. That's fine now. And so now our nucleophile will attack in the less hindered position. So those are the main features of alkaline versus acidic conditions. But please, please get practice being able to tell, based on what you're given, whether you're under alkaline conditions or acidic conditions. And this will not be wasted time. We will need that big time next term. Other than that, I can't really think of anything else. Well, I mean, I do want to talk a little bit about thiols and sulfides, etc. And then we'll do our reef session, and then we'll call it a day and a week and a semester. And we'll pick up where we left off in the spring. Good, well, just a couple other things then. Why don't the protic species hinder the SN2 reaction in this example? Well, remember, you can do an SN2 reaction in a protic solvent. We never said you couldn't. The opposite now, you certainly could not do an SN1 reaction in a polar A protic solvent. In a polar A protic solvent, you're never going to get the carbocation that you would need. But you can certainly do an SN2 reaction in a protic solvent. It just is slower than if there were no protic solvent. So that's why. The reason the protic species doesn't hinder it is because protic solvents do not forbid bimolecular reactions. And we never said they did. We just said they're slower in protic solvents, other things being equal. But these would all work just fine. Good. So with that, I just basically want to refresh your memories on the sulfur analogues of all of these things. We already mentioned thiols. These used to be called mercaptans, by the way. But thiols are the sulfur analog of alcohols. And one thing that's important to be aware of is just as you can use an alcohol, you can deprotonate an alcohol and react with an alkyl halide, preferably primary, to make an ether. That's the Williamson ether synthesis. You can do the very same thing with a thiol. So if you took, for instance, this thiol, let's say, and let's say we treated this first with sodium hydroxide in water, since, again, that's going to be more than strongly alkaline enough to deprotonate a thiol. An alcohol, not so much, but that would certainly deprotonate a thiol quantitatively. And you would get the thiolate ion. And now let's say, just because we can, that we treated this with benzyl bromide. Well, that thiolate ion is an excellent, excellent nucleophile, and that will have no trouble, again, undergoing an SN2 reaction with this primary alkyl halide, and you would get, in this case, what shall we call this? How about benzyl isopropyl sulfide, something like that. And so that's just a Williamson ether synthesis. There's nothing else you have to know besides the Williamson ether synthesis. This is the same thing. All we've done is changed the oxygen to a sulfur. And you can certainly use the same type of process in order to make a sulfide, which is the next one. I just want to remind you that thioethers, as they're also called, we usually call these sulfides. So they're the sulfur analog of ethers. But you can easily make sulfides just as you can easily make ethers. And R1 and R2 can be the same or different. I thought while I was at it, before we go to our reef pulling, since we're talking about all of these sulfur-containing functional groups, I just wanted to remind you of some of the others. Another one that shows up in biological systems, particularly in the shapes of proteins in the form of cysteine bridges, is the disulfide functional group. It's kind of the sulfur analog of a peroxide. And while we may have more to say about this in detail later, it's possible to go in both directions. You can reduce a disulfide in order to get 2 molecules of a thiol. And of course, there are also biological reducing agents that will do that for us. Things like NADH, FADH2, things like that can be used to get that reaction to go under biological conditions. And likewise, you can just as easily oxidize two thiol molecules to get a disulfide. That's again involved in cysteine bridges where the SH groups on two cysteine residues in a protein that can be very far apart from one another, by the way, but they're brought close enough together and they oxidize it and they connect this disulfide group. So another place where disulfide linkages matter is in the proteins in your hair if you get your hair permed. Do people still do that? I don't know. That was big in like the 70s and 80s. My mother would go to get her hair permed. I just wish I had enough hair that I could get it permed if I wanted to, which I don't, but I wish I could. Anyways, so be that as it may, that's another thing that we'll, I think, talk about more in the chapter on amino acids and polypeptides next term. Oh, still in the 90s, people were, that's actually, I had a colleague, a male colleague at my previous school who always had this big perm going on. It's fine. Good, so while I'm at it, before we get into our reef session, I just wanted to point out a couple more of these more oxidized sulfur-containing functional groups. One of them that we've actually met already is the sulfoxide functional group. So we're already familiar with dimethyl sulfoxide, where R1 and R2 are both methyls. That's the smallest possible sulfoxide. So that's a more oxidized sulfur-containing functional group. And then you can do the same type of thing again. Go from 10 electrons around sulfur to 12. And that type of compound is called a sulfone, S-U-L-F-O-N-E. So I don't know how much we're going to use these in the future, but I just thought you should at least see what those functional groups are called. You don't run into either of these very often. But these more oxidized forms of sulfur certainly do also exist. One thing to be aware, I think you're all familiar with how thiols and sulfides smell really bad. If you've ever smelled a skunk, then you've smelled those. And that's one thing I think you'll notice in general, is whenever you've got a compound that has sulfur in the -2 oxidation state, that's as reduced as sulfur can get. And anytime it's in the -2 oxidation state, you're gonna have unpleasant smells. As the sulfur gets more and more oxidized, those smells tend to go away. But certainly thiols and sulfides are gonna have that really rank, disagreeable type of odor. Good, so other than that, I think that's all I really needed to say in terms of class material. That leaves us a few minutes to do our reef pulling session, which is fine. And other than that, I mean, we're done, but we're not really done. Because especially those of you who have me next term, we're just gonna pick up right where we left off. At least as of this moment, it can always change. It looks like it'll be completely online. So I'll basically do much the same thing, except from my house. And you may or may not occasionally see a cat, which is good. And that'll be basically it. You'll just zoom in.